Let me try to explain NMR from a basic theory standpoint. Then I will discuss two of the four main features of an NMR spectrum: the number of signals and the integration, which actually gives us the number of hydrogens per signal. Let me remind us about the limitations of an IR spectroscopy before we talk about NMR spectroscopy. Let's say we have an unknown molecule, but we do know the molecular formula because we could do combustion analysis. And we figure out that there are 3 carbons, 8 hydrogens, and 1 oxygen. By this point, you should be able to draw all the constitutional isomers of this molecular formula, and 2 of them, let's say we narrow it down to these 2 structures. An alcohol, you should know that when you draw the constitutional isomers of an alcohol, they include ethers. They would have the same number of hydrogens as well. Okay. Just double check the count, 8 hydrogens each. Well, IR is great and really quick to figure out the difference between these two because they have different functional groups. So the IR spectra, or the spectrum of each of these, is going to be very distinct, and you could match whatever spectrum you have. If it shows a OH signal, then it's the alcohol that you narrowed it down to. Or if it doesn't, and it just has maybe a carbon-oxygen single bond signal, then you're going to go with the ether. Okay. Well, actually, before I tell you the I promise you the limitations. Well, what if you know that it's an alcohol, but there are 2 isomeric alcohols, constitutional isomers, with the same with that molecular formula? IR cannot because they have the same functional group. Now, yes, there may be an expert who can look at the fine details of the IR spectra and figure out the difference between these 2, but they both have hydroxyls, they both have a methyl. To me, I wouldn't be able to tell. They would have the same signals in approximately the same locations. Okay. So IR for me, is not good with this, but NMR is. NMR can definitely tell you the difference, and you could put these puzzle pieces together with a little bit of practice. Okay, now the basic. Actually, before I tell you the how of NMR, let me tell you the wow of NMR. Crickets. I'm going to give away the climax, the ending. And the ending is this. Those are NMR spectrum, or spectra. And they are the NMR spectrum of these 2 alcohols. Now, it may look like hieroglyphics, like how am I supposed to figure out which is which? Well, let me show you this. NMR, you're analyzing the proton. A proton is the nucleus of a hydrogen atom, right? No neutron. Here's the model for 2-propanol, the one on the left. The environment, you could call it the chemical environment, but later on we'll call it the magnetic environment of this hydrogen, looks the same because of rotation. Looks the same as this hydrogen here. Looks the same as this hydrogen here. So what I'm saying is that as this is spinning, all 3 hydrogens see the same thing on average. But the thing is, because of symmetry, these 3 hydrogens on the right also see the same things because all I have to do is flip the molecule and I'll get the same chemical environment or magnetic environment as these other 3 methyl groups. Long story short, these 3 hydrogens, and I'm going to use the word proton from now on, these 3 protons have the same chemical environment. They see the same thing on average as the molecule spinning as these 3 hydrogens on this methyl group. Okay, you have a hydrogen in the middle, and that's definitely a different signal because it's closer to the oxygen, and you have a hydrogen here because it's actually connected to the oxygen. ABC, you expect 3 signals. Okay? Take a look at one propanol. Let's do the same analysis. The methyl group is definitely going to be different than the CH2 group. But look at these two CH2 groups. This CH2 group is closer to the methyl. This one is closer to the oxygen. They literally see different environments. They feel different magnetic fields. And then we have D here. 4 signals. With just that, if you have to do a matching exercise, this is 4 signals. So here we have 1, 2, 3, 4. So yes, I know that this is one signal, but that signal is split into 3 peaks. We will talk about splitting in a different video. But basically, I have 4 signals. Take a look on the other side. 1, that's a signal, and that's a signal. Okay? So this dude is to this spectrum, and this one is to this spectrum. They match the number of signals. Okay? And if you're curious, well, no. I'm not going to assign which signal is A, B, and C, and which one here is A, B, C, or D. We'll do that most likely in a different video when we talk about chemical shift. Okay, so that's the beauty of NMR, and you'll be able to do this, in a short amount of time. Okay. We'll go back to that spectrum a bit later, and I'll show you the 4 features, because today, or in this video, we're only going to look at the 2 features. But now, theory. Why does this happen? Why do those protons have different signals, or show up in different signals? Okay. Oh, by the way, in a different video, I'll tackle feature 3, which is splitting. Talked a little bit about that, right? This signal, I know it's kind of hard to see, but that is 3 separate peaks for one signal. 4 signals total. Splitting, and number 4 would actually be the location of the signal, called the chemical shift, in a different video. Theory. A little bit of physics, high school physics, because we are dealing with magnetic fields and electrons creating a current. We'll call this basic theory. And let me draw us that molecule 1 propanol. I'm going too fast. You could always pause. Do I have all the hydrogens? And I'll put lone pairs. Okay. Each of these hydrogens has a proton that can spin. When that proton spins, it creates a mini magnetic field. The idea of the NMR experiment, and I'll go over NMR, the abbreviation, nuclear magnetic resonance. I'll get to that in just a bit. We have an external magnetic field. I bet a lot of you have been in an external magnetic field in the same exact type of experiment, because those who have taken an MRI scan, magnetic resonance imaging scan, you are lying down inside a giant magnet. Same thing with our molecule samples. It's going to cause these protons, the hydrogen protons, to spin in such a way that they will create their own mini magnetic field. Let's take a look at this hydrogen here. Maybe that hydrogen is making a magnetic field going down. That is against the magnetic field, the external magnetic field. And if you remember your quantum numbers, we're going to have a spin down as -1/2. Oh, just be careful. I shouldn't have said quantum numbers because that applies to electrons. But the spins of hydrogen, the proton itself, can be +1/2 and -1/2. Let's take a look at, I'll use purple. Let's take a look at this hydrogen. It makes a magnetic field with the external. in the same direction. So initially, when all of these mini magnetic fields are not in a magnet, they will be randomized. They will point in all different directions. Okay? But under the magnetic field, you will get a population of spins for a particular proton that are against, I'll still use the term 1/2, a spin of negative 1/2, and a spin that is with or aligned. I should have said aligned. And then we'll call that positive 1/2. So obviously you have more than one molecule. So in your billions and billions and billions of molecules in sample, this particular hydrogen, half of them are going, half of them are going with the magnetic field or making a magnet against the magnetic field, and half of them are with the magnetic field. There's only two states. I think that's the most important part. There are two states when you apply a magnetic field to the molecule. State 1 and state 2, and they differ by some energy difference. That's the setup of NMR. You put the molecules in a magnet and get these spins aligned with or against the external magnetic field. So again, once we have this in a magnet, let's say we have schematically maybe 3 hydrogens, I did that wrong, 3 hydrogens with the spin minus 1/2 or against, and let's do 4. Don't worry too much about the numbers, but I want them different. 4 with the external field, because there is a slight excess with the magnetic field because it's lower in energy. All right, so we have this set up in the spectrometer, and we hit it with electromagnetic radiation. I should have reminded us that this is all based on electromagnetic radiation absorption. In IR, we were absorbing light waves that are in the IR region to what? To correspond with the vibrations. NMR is actually radio waves that correspond to the flipping of these proton spins. I haven't talked about the flipping yet. Let me show you what happens here with a flipping of a proton spin. You hit it with radiation. The radiation frequency is around 3 times 10 to the 7 hertz or inverse seconds to 9 times 10 to the 8 inverse seconds. That is a wavelength of very long, actually, 10 meters to 0.33 meters. Remember your equation? Speed of light equals wavelength times frequency. That's how I got the wavelength. When you hit this, every down spin or negative 1/2 spin will flip up. Every up spin will flip down. So you flipping the spins of the protons. Okay. It's absorbing energy. So depending on what your particular proton is feeling magnetically, what its neighbors are doing, right? Look at all the different effects. This proton is feeling the effect of the external magnet. It's also feeling the effect of the neighboring hydrogens. They're close enough that they will affect each other. Well, that will change how much energy is needed to flip the spin. Let me write that. Protons, and again, those are the hydrogens, in different, we'll say chemical environment. What atoms are around it, or that's the same as different magnetic environment, because now we're going to think of each of these protons as magnets. They absorb, or they have different energy gaps between spins that are negative 1/2 and spins that are positive 1/2. Those are the only two states when you're in a magnet for the hydrogens. So that energy difference is changed depending on which protons you're seeing, okay, or you're analyzing. And we saw with this molecule, we have four sets, A, B, C, and D. A, B, C, D. Okay. Now, let me get to the wording. Again, these different protons, these four different sets of protons will absorb different amounts of energy to flip their spins. That's what the spectrometer is measuring. And by the way, this range is radio waves. AM and FM, the same types. So yeah, you're hearing an AM FM radio, it is flipping your protons. The thing is, you're not in a magnet normally, so your protons are not aligned. So you have random orientations, you flip all of those, you still have random orientations. Okay, the wording, nuclear. Okay, obviously that refers to the nucleus of the proton in this case. The, the, the nucleus of the hydrogen, which is a proton. Magnetic. Oh, yeah. To set up the experiment, we've put the protons, the sample, in a magnetic field, and then we start flipping them with radiation. Resonance. Resonance is an interesting word. Resonance is the absorption of electromagnetic radiation by it's called a precessing, not processing, a precessing nucleus and its resulting flip. What? Okay. Let me try to fit it onto this page. Because let's say we have this spinning proton, which creates a magnetic field going down. So the spinning proton actually is spinning this way, counterclockwise, from physics, right? If you know the direction of the current, you know the direction of the magnetic field induced by that current. But when we flip, right, we're going to flip it going up, and we now have the rotation this way, I believe. The thing is, you are cutting out a cone as this spin flips from going down, what's the intermediary? Let's go like this way, to going up. So as this is rotating, you're cutting out a cone. It's called precessing. So the cone shape is the precession of this nuclear spin. Don't worry about that. Resonance, you have different resonances because your proton is absorbing at different electromagnetic radiation wavelengths. Nuclear magnetic resonance. Okay. Let me get to a couple of things about the actual NMR spectrum. Let's take this molecule here. Let's apply some of what we've talked about. Number of signals. Number of signals. Well, the thing is, this is symmetrical. If I take this molecule, let's say it's my calculator, and I flip it, you should know that those methyl groups will end up where these methyl groups are. This molecule's flat. This is a benzene ring. So I have a signal for the methyl groups, okay, but they are equivalent methyl groups. And you know that there's a hydrogen, right, on each of these carbons. Again, due to symmetry, all of these hydrogens are the same chemical environment. Okay. And we have the beginnings of a spectrum. Now, The x-axis is ppm, parts per million. Okay, you know ppm. Maybe if you took environmental, biology, or chemistry, parts per million of toxins in the air. It's very low, 1 part per million, 2 parts. What the heck is that? Well, first of all, it goes from 0 to 10, from right to left. Sometimes it could go up to 12. It's very rare to have a signal at 12, but sometimes you do. You have a standard, tetramethylsilane. That usually occurs on every spectrum because it helps the chemist make sure the scale is correct. And they shift the scale to make sure that TMS is 0. So how many signals do you expect for this molecule? You expect a signal for A and a signal at B. Don't worry exactly where I put this, but I'm going to call the one on the left B and the one on the right A. The chemical shift, like here, this is maybe 1.1 ppm. That is called the chemical shift, and its symbol is that. So symbol that equals 1.1 ppm. Unit, symbol, the name. This represents the difference in resonance frequencies between the two sets of spins. A population of spinning down against the field and spinning up with the field. And it's small, 1.1 parts per million. So there's an excess of, see, the up spin is the one that is a little more stable. So there's a slight excess of the purple. Don't worry about that. Do not worry about how to convert the population to ppm. What it just means is that based off of TMS, tetramethylsilane, this signal is at 1.1, and maybe this signal, we'll call this at 7.5. Okay. But it comes from the fact that there's a slight difference in the populations between the, we'll call this a downspin and the upspin. Not a big deal. But what eventually you want to get to is interpretation. And we are looking at, in this video, the number of signals and integration. Okay, so how to practice this? We already did a little bit of practice here, counting the number of signals. So let me give you some examples where you have to be able to use symmetry to figure out which signals are equivalent. For instance, this molecule here. And remember, you're only labeling the hydrogens, or technically the carbons that have hydrogens, because for line drawing you don't see them. Take a look at this. I'm going to call that methyl group proton A, but as this bond rotates, those sets of protons will look exactly the same as these sets of protons. So we have A and A. B for that hydrogen right there, C, D, and E. C and D are both CH2 groups, so why am I labeling them differently? They're both next to a carbonyl group. Well, this C doesn't feel the effects of this chloride or this chlorine atom as much as this CH2. So D is closer to Cl, C is closer to the isopropyl. They're different. 1, 2, 3, 4, 5 signals. Okay, you would predict that this molecule has 5 signals. What about a double bond and a ring? You want to give this a shot before I go over the answer? How many signals would you expect for this molecule? A, B, don't forget this one in the middle, C. This is a CH2D, this is a CH2E, and I'm going to tell them that they're different because this D is feeling the effects of the double bond stronger than this E. The D is closer. This is F, another stage 2. It's definitely different than E, and E is different than D. But you got to remember, when you have a double bond, especially, well, in a ring, those two H's are different. Technically, H is a little bit closer to the methyl group, and it's always closer to the, ethyl group. It's always closer to the ethyl group than this hydrogen. So that will always see a different environment than this hydrogen here. One more. A ring now, and let me give us 2 double bonds in the ring. Where do we start? Let's start here on the left, A. Now we have a proton here, that's B. This is symmetrical. So if I take this molecule and I flip it this way, look at where my thumb is. That's proton B. If I flip it this way, oh, it's on the bottom now, right here. The B's are identical, but B and C are not identical because C is closer to the triple bond. But this C is equally as close, and C is the same thing as this C. Remember, there's a hydrogen at the end of the triple bond, if it's terminal, D. We expect 4 signals from here. Just from the signals, we have 4 features. Just from the signals, you could eliminate a lot of spectra, but also you could eliminate a lot of guesses. Let's say you're given this spectrum and you have to guess what it is. Well, all your guesses better have 3 signals. Okay. All right. So that is the number of signals. I promised us the second feature, integration. Okay. And that is the number of H per signal. Because if I ask you how many hydrogens are for signal A, you will say you have 6HA. For B, you have 1HB. For C, you have 2HC. For D, 2HD. For E, 2HE. These numbers right here come from what's called the integral. And you get the integral by doing an integration. So what's an integration? Here's a real spectrum. Each of these signals, okay, we have 2 spectra here. Each of these signals has an area. You could almost color it in. There's some space. There's some not volume, but there's an area underneath the curve. When you do calculus and you take an integral of a curve, you are expressing that area as a number. So they're telling me that this area is about, about twice as big as that area. A little bit more, actually. 54 and 23. Well, that ratio tells you the number of hydrogens per signal. But for this one, we don't have a molecule that has 54 protons. So let's sketch that out. We have a signal here. So I draw it as a line, but it's actually a hill. And I have a signal here. Okay, they're all 1 peak per signal, and we have here. The numbers were this. Actually, when you take an integral, again, the machine is taking the area underneath each curve. Okay, and you'll see it something like this. And the height of each integral gives you the ratio. But the ratio here is kind of tricky because the numbers I see on my study sheet, okay, 54, 23, 33, 54, 23, 33, those are the ratios, but those are not the number of hydrogens. If I know that I have, let's first say, 10 hydrogens, I don't know that, and maybe I don't know this, but I know 10. the integrals should equal 10, should represent 10 hydrogens. So how do I do that? I divide it by a common factor. So if I divide this by 11, it's going to be approximate. I get 5. If I divide this by 11, let's say it's 22, I get 2. And if I divide this by 11, I get 3. This is literally telling me that this signal represents 5 hydrogens. This signal represents 2 hydrogens, and this 3. That's where I'm getting those numbers. So there's a ratio of 6 to 1 to 2 to 2 to 2. Here I have 5 to 2 to 3. Now you may ask, what the heck? How can I have 5 equivalent hydrogens? It's a little bit tricky, but 5 equivalent hydrogens could be something like this. Now, is it truly 5 equivalent hydrogens? No. We know that these two are different than these two and it's different than this. It's just that the chemical shifts are so close that they kind of overlap each other. And if you see a 5, you're going to assume that it means the 5 hydrogens of a benzene ring. Benzene ring should have 6 hydrogens. This tells me that I have one substituent, because one of the hydrogens was replaced by a substituent. It is that kind of puzzle piece putting together that you will develop. Okay, we'll get more practice later after I've gone over the next 2 features of an NMR spectrum. But do you see how powerful it is just by knowing the number of signals and by knowing the integration? Because now, ooh, what is that? If you have a 3H signal, think methyl. You have a methyl group, CH3. Whoa, what is that? You have a CH2 group, CH2. Put those two together, you have this group right here, ethyl, CH2, CH3. This is a puzzle. You're identifying certain pieces, and then you're going to put them together to create a molecule that is consistent with your NMR spectrum. I will see you in the next video where we talk about splitting and chemical shifts to round out our ability to interpret these type of spectra.